Welcome to today's Explainer. Usually when we think about history, we're thinking in terms of sweeping decades, right? Or maybe monumental years. But we rarely stop to think about the absolute power of a single calendar day. Following the structure outlined in our source document, ENG, we're going to see exactly how May 23 is, without a doubt, one of the most incredible dates in the history of mathematics. But hey, don't worry, we aren't just going to stare at dry equations today. We're going to dive into how this one specific date literally gave us the modern, interconnected, high-tech world we live in right now.
Okay, so let's take a quick look at this timeline, because on this exact date, spread across completely different centuries and entirely different countries, a group of absolute mathematical detectives was either born or left their final mark on the world. And the truly crazy part? These folks probably had absolutely no idea their work would ever intertwine. Yet, working totally independently, they all contributed to the exact same technological future. Let's meet them one by one.
Now, we use our smartphones constantly, but have you ever wondered how they easily display millions of colors and complex 3D graphics? To really understand how they work, we gotta look past that smooth glass and dive deep into the math. Just think about it for a second. Whether you're endlessly scrolling through a feed, watching a high-def movie, or playing a super intense video game, your screen is instantly organizing millions of tiny dots of light, updating them 60 times a second or more. How on earth does your device know exactly how to shift and change all those colors in a fraction of a second without just completely crashing?
Well, the answer actually goes all the way back to May 23, 1901, with the birth of John Williamson. He was a Scottish mathematician who absolutely mastered something called the theory of matrices. And look, you definitely don't need a math degree to get this. Just think of a matrix kind of like a massive spreadsheet, where every single cell controls the exact color and brightness of one individual pixel. Williamson figured out the intricate shortcuts needed to calculate and manipulate those massive mathematical spreadsheets instantly. Today, our computer processors use those exact same matrix rules to render the stunning graphics we carry right in our pockets. Every pixel on our screens is secretly arranged by matrix math. While his colleagues back then probably just saw a guy churning out a stream of dense academic papers, what he was actually doing was writing the literal rulebook for our digital worlds. He took something mind-bendingly complex and gave our computers a simple set of rules to paint the vivid landscapes we love getting lost in. So every single time we play a game or stream a show, we are directly relying on his amazing discoveries. Pretty wild, right?
Moving right along our timeline, we fast forward exactly 27 years to May 23, 1928. We're leaving the illuminated world of pixels and plunging straight into the invisible highways of data, where another brilliant mind is about to completely bend the rules of space. Which brings us to a huge question. Why does our internet connection smoothly route messages across the globe without getting hopelessly tangled? I mean, it feels like pure magic when a text travels the world in a split second, doesn't it? Our data is broken down into tiny packets and sent flying across this incredibly chaotic web of cables, satellites, and cell towers. With billions of devices connecting at the exact same moment, why doesn't the whole system just tie itself into a massive knot and shut down?
The answer brings us to Ioan James, who was born on May 23, 1928. He spent his life unraveling a deeply fascinating branch of math known as topology. If you haven't heard of it, topology is basically the math of flexible shapes. Think of a subway map, right? It doesn't actually matter if the physical tracks curve, zigzag, or go perfectly straight. The only thing that truly matters is how the stations connect to one another. Instead of measuring rigid angles, topology looks at how networks can be stretched and bent without ever losing those fundamental connections. The shape of our digital world relies on the math of flexible networks. That flexible geometry is exactly what keeps your streaming movie playing even when a cell tower suddenly drops offline. Because our digital networks are constantly shifting and changing, engineers use the flexible math of topology to design robust internet structures that can bend without breaking. So, thanks to Ioan James's work, our data always finds a clear path home.
Okay, let's jump forward again on our timeline, this time to the year 2005. The challenges facing humanity were growing exponentially, and this next May 23rd milestone takes us beyond Earth entirely, looking at a challenge that is literally a matter of life and death. How do astronauts survive extreme invisible radiation while living aboard the International Space Station? Space is an incredibly hostile environment. Up there, astronauts don't have the Earth's thick atmosphere to protect them, so they're constantly bombarded by high-energy particles traveling at mind-bending speeds. If we can't even see this radiation,
how do we know exactly how thick to build the walls of the space station? How do we protect them from an invisible threat? Well, we sadly lost the brilliant Kazakhstan mathematician Umirzak Sultangazin on May 23, 2005. But he left behind something absolutely crucial. He perfected kinetic transport theory, directly shaping the safety protocols for our most ambitious space programs. Basically, he mapped the chaos of deep space. His theory allows us to calculate what is essentially a massive cosmic game of billiards. He developed the complex equations that accurately predict exactly how high-speed invisible particles will scatter, bounce, and absorb when they hit a physical barrier. Our journey into space is guided by the math of invisible particles. And his equations didn't just stay stuck on a dusty chalkboard. As a director of research, his mathematical models were put to the ultimate test on the Mir space station, helping engineers design the exact physical shielding required to keep astronauts alive. Because he mapped out the math of how radiation behaves, space agencies can ensure long-term human survival in the cold vacuum of space. It's a real game changer. Moving to our final stop on the timeline, 2015. We've seen how this one date gave us the math for screens, global networks, and surviving space. But this final connection, it looks inward, at us. We're moving from the physical world straight into the realm of human behavior. Why do competing apps, companies, and even our AI assistants seem to predict exactly what we want? We make thousands of decisions every single day, but have you noticed how the world around us just seems to perfectly anticipate our next move? Whether it's an algorithm flawlessly suggesting the perfect video, ride-sharing apps seamlessly adjusting prices in real time, or companies pricing their products in a fiercely competitive market, it all feels incredibly coordinated. How can a cold computer model accurately predict the sheer chaos of human free will? The answer lies with Nobel-winning mathematician John F. Nash, who passed away on May 23, 2015. He established the mathematical principles of game theory, giving us a revolutionary concept called the Nash equilibrium. Nash essentially proved that when people or companies or even computer programs are competing against each other, they'll eventually settle into a predictable mathematical balance where no one wants to change their strategy because doing so would just make them worse off. It completely transformed economics, and today, it's the exact math algorithms used to predict our choices and optimize massive digital systems. Our daily choices are secretly part of a massive mathematical game. Now, it might sound incredibly abstract to say game theory is the key to economics, but in reality, it just means human competition isn't random chaos. Whenever an AI decides which ad to show you or dynamically prices your next flight in a split second, it is essentially running John Nash's math. He proved that human competition is a massive, intricate game with definitive rules that we can actually calculate. Looking at this full timeline now, every person we met today, spanning across different centuries and hailing from Scotland, England, Kazakhstan, and the United States, all asked the exact same question. They were either born or passed away on May 23rd. But the true thread that connects this incredible spread of history is their unyielding curiosity. What is the pattern hiding inside the chaos? Because they dared to ask that question, our world today has beautiful smartphone screens, a resilient internet, safe space travel, and incredibly predictive AI. Math isn't just numbers written on a chalkboard. It's the invisible architecture of our entire reality. So looking at the incredible legacy left behind on this one single date, I have to ask, what pattern